Again, thank you everyone for joining today's webinar, 10 Steps to Use PLM Tools for Dimensional Engineering. Please note that you've joined as an audience member and are muted. My name is Madeline and I'm today's moderator, and we're going to begin with a quick overview of our agenda. We'll start with a little bit about Geometric Solutions, who we are and how we can help you. Then we'll jump into our main topic, 10 Steps to Use PLM Tools for Dimensional Engineering. Our presenter today is Curtis. He has more than 30 years of experience in manufacturing technology and has been at the forefront of digital simulation, specifically related to virtual prototyping and dimensional quality. He is recognized internationally as an expert in digital simulation using 3D tolerance analysis simulation tools. He has experience using all the major CADs, PDMs, CAE systems, and multiple digital simulation applications. And as you can see, Curtis enjoys the blending of new technology, software, and best-in-class processes, all while driving the need for quality, resulting in the reduction of overall costs. As per a quick intro to who we are at Geometric Solutions, we're part of the Waltonen family made up of 3 companies located throughout the Midwest: Waltonen Engineering, Independence Tooling, and Geometric Solutions. Our story is pretty simple. Waltonen develops innovative engineering solutions using Siemens software, and we got so good at it, Geometric Solutions started selling the same potential for success in the form of Siemens software. So when it comes to implementing and optimizing these solutions like an expert, Geometric Solutions can get you there. And now I'm going to pass it off to Curtis. Curtis, take it away.
Great. Oops, went backwards. I'm just going to add one more quote here. The president of our company has said that our ability to successfully partner with our customers comes from our experience in using the tools every day. Waltonen Engineering is our parent company. We use these tools every day. So we're speaking from that. In fact, there's a case study in the handouts of Waltonen Engineering using the dimensional engineering process here that I'm going to talk about. So with that, we're going to talk about 10 steps to use PLM tools for dimensional engineering. So this is a dimensional engineering process, and we're going to talk about PLM tools that can help you get there. So I'm going to talk about a case study here. I don't know if you remember a few years ago, Samsung had a problem with phones burning up and exploding. Let's talk about that for a second. All right. When they actually started having this problem, they actually set up a 30,000 square foot facility that had racks and racks and racks of phones. They were root causing the problem. They were trying to figure out what caused it and why. So they did a lot of testing. What they found out was the way they make their batteries, there was 2 causes that kind of fell into effect here. In the corner up here, where the battery went together, the normal design should have been closer to a 90-degree angle, and the different layers inside they call it a jelly roll, and I'll talk about that in a second, should be laying flat. One of the problems they had was the case was a little small, there was some protrusions underneath, and it put a crimp in the corner, and that caused some of these layers to contact each other. In addition, a normal designed roll here has the negative electrode, which is this gold colored part here. They should never cross over the top of each other, but due to variation, some were longer, the way they packed it, the process put variation in it and had that overlap. So it became a problem. So what it did was it caused, oops, come on, there we go, a recall. If everybody remembers that, they had over 2.5 million phones out in the public when they made the recall, and they expected to sell over 19 million of these. So they went from producing 2.5 million and recalling them all, so they had the cost of that, but they lost the revenue on 19 million. These were $1,000 phones. If $500 went to Samsung, that's almost $10 billion in revenue they lost. But let's talk about what happened. 96 phones caught fire before the recall happened. 13 people got burned. 47 people had some damage to property because the fire started. 2 caught fire during flights. And that actually, got these phones banned from flights. And Samsung actually opened up, service centers inside airports so customers could get a refund or trade in for the device before a flight. That's how bad it was. What did it do? it literally cost billions of dollars, damaged the corporate name, lost customer loyalty, and this is a unique one, changed federal law. You know, this, when we go onto airplanes, you know, there's questions about batteries. It was because of this. So, you know, this was a very strong recall if it changed federal law. The other thing that really hurt, the estimates were 5 to 7 million Samsung users would be switching to iPhone or the Google Pixels. So they lost customers too. Very expensive recall. But it could have been avoided. Using a full dimensional engineering process and some of these PLM tools I'm going to talk to you about, they could have found the problem and resolved it before it actually hit production on the plant floor and got delivered to customers. I'm going to turn my video off here just for a quick second so I can just make that blown up. There we go. All right, so it could have been avoided. So let's just talk about it. What we're going to talk about specifically here is for dimensional engineering and dimensional quality, not just quality, but dimensional quality. So it could be functional. It could be, this happens to be a jet engine there, but as we go around here, the clearances around these things, we don't ever want them to touch, but we want them small so they can create pressure going through there. You know, so it's a functional requirement, but there are dimensional requirements that have to be met, and the quality engine is dependent on these dimensions. Similar to that phone, some of the dimensions and the way things were made it not function properly. Could be aesthetic, cars, gap and flush. You want them consistent, you want it even, you want them parallel. When you look down that hood, the fender, you want a nice parallel gap. If it doesn't look parallel, it looks like it's a poor quality vehicle. It might perform great, it might do everything else great, but it doesn't look right, and it's aesthetic, and the consumer doesn't like it. It could be a function of another requirement. Here I have a wing with dual flaps, and we're trying to do just a airflow, a CFD analysis of this for airflow. And what we're getting is amount of air that's going to be going between the primary and the secondary flap here. Might be a certain amount that has to be controlled. So that might be a dimensional requirement. You know, in this case, it might be 100 millimeters plus or minus 2 millimeters, whatever the case may be. But it's a function of another requirement. It's not because it's critical for anything else, but to make sure this requirement is met. So let's just talk about the pieces to this puzzle. Dimensional quality is many things, right? And there's different tasks done by different teams. So we have a product team. They do GD&T, they do tolerance analysis, they define datums. Hopefully they do objectives and build strategies, but we'll see. You know, manufacturing teams, they actually do prototyping. They would create locators. Hopefully they match the datums. They deal with scrap if it happens, and then they got a root cause and find out why it's happening. They make fixtures, and hopefully the strategy for the fixture matches the way that they designed it. You get into quality, you know, they design gauges. They actually perform inspection. They do PPAP and FAA. So, you know, PPAP, production part approval process, and or first article inspection, depending on what industry you're in. These are common things they do. They take that data and they record it and they store it somewhere. Service, they're the ones who deal with warranty and recalls. All these different tasks are done with different groups. In fact, if I look at like quality, the people designing the gauges might not be the people actually doing the inspection. You know, so these different groups within these groups are doing things. And the problem gets into is a lot of disconnected tools, a lot of disconnected processes. And what this dimensional engineering process is going to do is focus them all together and make one strategic process to follow. So the goal here is to win. That's what it is in business. You want to win. You want your company to be successful and to be competitors. But what we're going to talk about today is a plan for winning. So if we talk about this 10-step process, the foundation was based on Deming's plan, do, check, act process. For those of you in the quality business, Deming is the godfather, you know, the person who really introduced it here in the 60s and the 70s to the manufacturing industry here in the States. We take that and change it to a product life cycle. The plan goes to objectives and strategies, so it's our plan. Doing it is releasing CAD and drawings. Checking it, well, we have to have checking systems. And act, well, we do root cause analysis, find out what's going on, and then it goes through this loop and it's iterative, and we'll talk about that a little bit. But what we've done is taken this 10-step process and applied against it. So the first 3 steps are in the planning / objective and strategy stages. We're going to go through each one of these in depth in a moment, but we got objectives, strategies, and analysis. And we do that up front before we do anything else. We want to make sure we can meet our objectives. Then we get into the next phase, the doing, where we actually release GD&T and PMI and defining measurement points. Then we get into the checking, which is the measurement plan, and we'll talk about the difference between plan and points. Checking systems, the actual making of the gauges, and then the physical inspection. And the last couple steps are the root cause analysis and documenting lessons learned. So we're going to talk about these 10 steps, what they are, and PLM tools to help you get there. So our first poll question: have you ever had to travel to a plant to solve a quality problem?
Looks like our top answer is most programs at least once.
Yeah. I can state in one of my prior careers, I was one of those gold frequent flyer guys. I really got really good at problem solving, and they kept sending me to different plants because problems would arise every week and somebody had to help figure out how to solve them. So, you know, it's quite common that we're fixing things at the tail end where this dimensional engineering process will help solve that before it becomes a problem. So let's look at these steps, right? So here's the 10 steps. I'm going to go into the first one here, build objectives. Build objectives basically describe what the allowable build variation that can happen and still can be considered, you know, acceptable, right? Depending on who you talk to, if you talk to marketing and you talk to some of the product design team, they want plus or minus perfect. If you talk to the manufacturing team, they want plus or minus a lot. You know, it's somewhere in between. So what we have to do is create good values on there. It should be based on the voice of the customer. So I'm going to look at this door example here. You know, what we want to do is check the gap, flush, parallelism of that gap going across there, and they got specifications. If I'm building, you know, something, a cheap economy car, you know, I might have very loose numbers on there. But if I'm building something like a Mercedes Maybach or some very expensive car, maybe I want tighter ones because the voice of the customer, they expect the better tolerances. But I'm also got a more expensive product and I can spend more money to make sure I achieve that. So what we want to do is just document them. The way that we do that using PLM systems, I'm going to talk about Team Center here. Team Center has a product in there called Team Center Requirements. And what we're going to do is actually import a PDF, well, no, I'm sorry, Microsoft Word file. It can be a PDF. And it's going to read this document and document all the requirements that it reads out of there, which is really great. I can then report against it. And when I do tolerance analysis in the future, I can actually show how I do against that. And it can be talked about and discussed with the team, the product development team, to make sure we're understanding what's going on. So here we're just importing this in, it's reading it through. And this one actually had like 3,000 specs in it. And I'm going to open it up, it's done. And this happens to be a complete set of requirements for building a train. What's nice is I can go in there and I can actually edit it. When I edit it, I can actually save the different values and versions and know who changed it as time went on. But, you know, it is a complete document that has all the requirements. Now, these requirements are kind of listed in, you know, there's section 1, section 1.1, section 1.11, and that's what you're seeing here is it actually broke the door systems as a separate section, brakes as a separate section, because it's numbered and figured out that way. There's actually design requirements, they're all documented, so anybody can use them. Once I have those in my system, I can track against them. And it could be an Excel spreadsheet that I create, it could be something formal like this, but there's dashboards that go with this. So here I have a dashboard and I got different groupings And the different groupings are milestone 1, milestone 2, milestone 3, and 4. Where am I at in my process? You know, towards the end, I got to make sure everything's done, but I got to make sure I'm getting there. And my plan to get them done are achievable here. So here I'm going to break into one of those. So I'm going to go into milestone 3 and look at these. This happens, this is not a dimensional one, but there's accelerator and some road noise. I want to go into detail on that. I want to see where I'm at specifically on those, and I can get into that. So you can see here, you know, the green ones are met, the red ones failing, and the purple ones are not even been validated or checked. So I can see what they all are. In addition to them, I can see what the spec is, what the current value is, whether it's been evaluated, how we got the value, is it actual data, I got measurement from the plant floor, or I'm actually did a tolerance analysis. So I can see exactly what that is. I can see what the inputs are to that. So if I had like a 3D tolerance analysis model that I'm going to talk about later, did I use that? Where is it? You know, can I go validate that one again? So it's all tied together. They all talk together, one single source of truth. And it's all in a place that everybody can see and report back to. So Team Center with Team Center requirements is a great tool for documenting my objectives and tracking them to make sure we're on track. So let's just talk about objectives. You know, this is a cartoon, but you know, if we start talking about objectives, you know, you start talking to your customer or, you know, the marketing team that tells you what you want. Well, they explain it to you one way. The problem is the project leader kind of understood it this way. The analyst designed it this way. How the software code was programmed to support it. This is the one I love, how the business consultant, you know, described it. This is the important one, how it was documented, what was installed, how it was invoiced and billed, how it was supported, and lastly, what he wanted, what the customer wanted. Sometimes the customer doesn't explain it well. And just the process of documenting it will get a reaction from somebody in the team. If I documented this first, you know, thing up here, how I heard it being described to me, the customer might go, no, 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 that's wrong, right? But because it wasn't documented, it became an issue, you know. So what happens when the objectives are not documented? Any one of those executions would not have been wrong because there was nothing documented. And so we like to have, especially dimensional objectives, gap, flush, clearances, all that stuff documented up front as early as possible. Even if it's a placeholder because you don't know what the number is, put it in, get it documented, and then we can report upon it and make sure it is going to be met. So the next step is step number 2 here, build strategies. And this is a key element. These first 3 items here are the most key elements in the 10 steps. What the build strategies do is they describe your product and process enablers that guide how the parts will be designed and assembled. It's not just a product game, it's how you're going to put it together and manufacture it. It's your strategy, you know, it's your game, you know, how you play chess, the strategy, and how you move things around determines whether you're going to win or lose. The build strategies define how to control and put together the product to absorb, control, and hide variation. Variation's there, just where you push it. That's the important thing. We define things like slip planes to make sure the 2 parts, when they go together, can slip past each other. If 2 planes are butting against each other, we define which ones they are and make sure everybody agrees. The manufacturing team and the product team design their tools and parts that way to make sure it all works together. So it's a strategic way of doing things. So let's look at an example. So what we have here on the left is a tail assembly for an airplane. We take the skin off it, we kind of see a structure. There's a vertical, and then there's the horizontal here that goes from left to right. All right. If we go to the right, here's that vertical, and on the top, this is the center section of the horizontal. So one concept would have been was to build this piece with the holes in it, build this piece and build this piece, put the holes in it, and this could have been a set dimension based on the stack up. But what they've decided to do is they're going to put this hole into the blue part, put this hole in the blue part, pin them, and there's a slip joint here. So this green part and this blue part slide back and forth, from front to rear. And when it's in its fixture is when they rivet that together. So that's how they make sure that's a perfect, nominally set, consistent dimension, right? So what they do on the horizontal is they drill these holes and make them perfect. They take this assembly, drop it on, and then they use a reamer and they ream these two holes to match that. So that's the strategy. This hole is not put in until it's on the assembly. It's not put in the individual part. And so we make sure that the folks that are making this machining here know that, and the assembly guys know that when they make the tools to make that happen. So do you make dimensional objectives or build strategies and get consensus on them up front? Okay.
Looks like we had a clear consensus of we have design reviews for strategies.
Yep. A lot of folks do strategies, and but the strategies sometimes are not always focused on dimensional. If I don't have an objective, if I don't know where I want to be dimensionally, it's hard to make a strategy to make it get there. The goal of the objectives is to document what the customer needs. The goal of the strategy is to make sure I can meet those. Okay, so the next item here is dimensional analysis, number 3. So let's talk about that. Basically, we use it to predict if build strategy we can met. I take the build strategies, and I take the components, the design interfaces, the gaps, the slop, and the processing, and put it together. What we're going to talk about here is 3D Monte Carlo simulation, a product called VSA, works within Teamcenter, so it's a great PLM tool. But we can do Excel spreadsheets and stack up programs, many tools to do this. But you can see here in that simulation that's running on the right, I'm actually getting data to see how well that these holes line up with the parts based on the variation of the assembly. So what we do is we take, for the VSA tool to work, we take CAD from any type of CAD model. If we have GD&T and PMI already in the CAD, we use it. Otherwise, we'll build it. We add the assembly process. We calculate the measurements, which are basically our build objectives. We create a model, run the analysis, and it comes back and predicts how well we're going to conform to our objectives. That's the key. So here I'm failing my objective. That's terrible. What do I do? Well, inside the tool, there's a design of experiments feature that'll come back and tell us who contributed the most. So you can see one there, it's actually like 47%. It's the 500-pound gorilla in the room. I want to work on that. I want to see what that is. I want to try to make sure that that is not a contributor to my final results. It might be cutting a tolerance, but it might be redesigning it, especially if I'm doing it early. Here's an example of the tool in use. So the yellow part there is this is actually a shifter for a car, an automatic shifter. That green part is mounted to the cockpit. The lever pulls this cable out of its sheath, and then that sends a signal to the transmission what gear it is. We want to make sure that's consistent because we want to make sure the transmission knows we're in park when we really are in park. So you see Monte Carlo builds here, the actual model's wiggling just a little bit. And what that's doing is giving us data that we can analyze. So here I'm analyzing. You can see I got 3.3 millimeter range. We wanted plus or minus a millimeter, so I exceeded it. 8% of the builds fall in the red area there. So my design and experiments tool, here's that one at 47%, is right up on top. If I stand on it, it actually shows it on screen, and it's the plane behind that pin. And if that plane tips, the pin tips with it, and it pulls that shaft in and out from one build to another. So, it's a great tool. It's 3D. I can report on this. And then these results can be documented inside Teamcenter against the requirements. And if there's a question on it, we can actually pull this model up to make sure what version of the math or what version of the tolerances we used to make sure everybody's in consensus that it was right. Here's another reason we do it up front. This was a slice through a wing, and these are the dual flaps at the back end. And what the goal was the trailing edge of that wing, the very, whoops, sorry, hit my mouse here too fast. This trailing edge back here, they wanted to hold it at plus or minus 30 thousandths when fully deployed. The results of this model was like plus or minus 380 thousandths, 12 times as much. It was way out of spec. The interesting thing was 55% of the variation came from one tolerance, plus or minus 1 thousandths tolerance contributed over 50% of the variation in 380 thousandths. And I gotta look at my screen here. This little hole right here had that little tolerance, but it was on a short staff connector, connected to a larger connector, connected to a larger, and it just got exponential. This was done early on. This was a new cost-saving concept that they tried to put together. We tested the strategy and failed miserably. They redesigned it. You know, that's why we do it up front. If it's wrong, we can do what ifs and test it and make sure that it's right. If they would have went to production with this, they figured it would cost them millions of dollars to fix, where here, it costs us a few hours of time. So the first 3 steps, very important. We want to make sure those are done. In fact, if I only had to do 3 steps in the entire 10-step process, these are the 3 I picked, because they set everything up. If I don't do the analysis and know that I can meet my build objectives, I really don't care about the gauge, because the tolerances are bad and the gauge is going to say it's a good part, but I don't meet my requirements to sell it to my customer. So, you know, we'll talk about that a little bit more, how these steps interrelate, but the first 3 are the most important, because it comes down to this. It's all about money. You know, we want to make sure we are profitable. We want to make sure the products are robust and that we make a product that is usable. So let's talk about the next couple steps. GD&T and PMI is the next one. So what is GD&T? It's basically geometric dimensioning and tolerancing. It's the tolerancing that goes on your product. And you notice I got the word legal contractual documents, especially in a supplier-customer relationship. This is what gets you paid. If I can't meet the tolerances on a drawing, I might not get paid for my parts or my tooling. So it's very important to make that robust, that it works, but at the same time is achievable to be manufactured. It also provides the requirements for the corresponding measurement system, you know, whether it's vision, coordinate measuring machines, laser tracker, gauges, you know. But in essence, in its simplest form, GD&T assigns a tolerance to a feature relative to a datum. It just says this feature has to be plus or minus so much to something else and the shape of that tolerance zone. But in today's systems, CAD systems, all the major CAD systems use PMI. It's metadata, you know, that's applied directly to the 3D model. So it's not on a dead drawing, it's actually applied to the model. It also conveys other 3D attributes like welds, you know, surface finish materials, things that would normally go in a drawing, but you know, we're applying it to the 3D model. That's not just the pure geometry. And then it can be used in other things like CAM programming and CMM programming and inspection. There's other tools that will use this information. So days of old, we had drawings. Then when the CAD systems got a little better, we had, you know, 3D models that were linked to the drawings with associativity. And that nowadays, people actually put the PMI on the models and create a drawing for those who need a drawing. But the PMI is actually on the model. But a lot of companies I know and work with just put PMI right on the model directly, and they don't make drawings anymore. So it's, you know, but it's a tool that makes smart GD&T on the right, and the very left it's dumb GD&T because it can't be used other than by a human reading it. So started talking about PMI. There's other terms that are related to that, and I just want to talk about those. So PMI is the heart, right? It's basically non-geometric data applied to a 3D model. But there's terms out there called model-based definition. And it's typically the practice of the complete digital definition of a product within the 3D model. I'm actually doing all this stuff on 3D with more than just the GD&T. But then you have the model-based enterprise, the bigger circle. And it's reusing this information by downstream consumers across the enterprise. And that is the power that this 10-step process is working on with these PLM tools. They're talking to each other and they're actually being reused from prior work. So the next step on our process, number 5, measurement points. In this one, I've had most challenges on this process, but it basically identifies all critical points to be measured for parts or assembly. They're actually points going to be used by the metrology group. They're coordinated. And here's the key. They're children of the tolerances in the PMI. I apply a tolerance to a surface, and these children go with it. That way, when I'm downstream and I'm using this measurement point, it actually knows the tolerances. It knows where, how it's being defined. It's key in root cause analysis, and the goal here is to support objectives. If this is a fender on a car, and I have 3 sets of points here, I'm going to check the gap in 3 spots, on the final assembly. But now I got the data on the parts to support it. So let's talk about this. So, we go back to that door assemblies that we had before. So we got these objectives that we want to create. What we do is we take these 2 doors and we put coordinated points on both doors. You notice there's 3 sets, so I can check them in the same 3 spots on all cars. In some of the smart language here, the very end letter is a G or an F for gap or flush. Every company has their own standards on how they name things. But the key is they're coordinated, right? This is, especially needed when these parts are not made in the same part of the plant or totally different plants. Had situations where a supplier was making one of the parts and the other parts were made inside, and the supplier just picked the points that he wanted to use, or, well, they're not really coordinated. If I have a problem up here along this upper edge when I measure it, I don't have any data there. It's very hard to root cause it. And the goal is to be able to root cause. I got my goals, my objectives, and I got my tolerances, but if I don't have a way to root cause if there's a problem, it becomes an issue. So having this coordinated and documented as points in the PMI under the tolerance, being a child of the tolerance of those features, is needed to make sure that I can support this all the way through this PLM process. So this is a question. Do you coordinate measurements between parts?
Looks like our top answer is we leave it to the quality control team.
That's quite common. People make a drawing and then it goes to the quality folks and they do it. Hopefully it's coordinated. Hopefully, when I do these individual pieces, they work together. Even if I make everything in one plant, I might have different quality control teams because some people are inspecting the parts on the floor. Some go into the QC room. What they measure, how they measure it, hopefully it's coordinated, but not always. And where it really makes a difference is in the root causing later when there is a problem. I need to have the coordination to make sure I can fit together. So going back to our 10-step process, number 6 is our measurement plan. Now, measurement points were the actual points, but the measurement plan is the strategic plan for validating things. The type of measurement devices. Do I use something like this coordinate measuring machine that's here? Do I use hard gauges? When am I going to have the gauges? At prototype, production? What's my supplier strategy? And then frequency. Do I require 100% inspection? 1 a shift, 1 an hour, 1 a week? And that all makes a difference. It determines your budget for investment and manpower resources. So we want to get this up front and make sure everybody agrees upon it. We have budget for it. We plan for it. It's not an afterthought. A lot of companies, they get down to their, their final end of it and they start getting their program ready. And oops, we don't have any money for gauges. So they're all going to go through the coordinate measuring machine because I don't need gauges. but then it becomes a bottleneck because it's one machine checking multiple parts and it's one at a time. So talked earlier about measurement plan and the points or the measurement points. You notice this is actually hitting specific points. These points hopefully are coordinated to the measurement points that I had earlier. So it's, making sure that we can do it properly. So there's different types of gauging methodologies. We have vision. This happens to be on a robotic head that goes in. I can do 100% inspection. It's very fast, but I have to invest in a robot. I can do something like this, a little cheaper investment, but it's sitting out by the floor. It's a gauge. They put the part on, hit some clamps, do some quick checks. They can do 100% inspection, but it takes up floor space. If I look at this one up here, this happens to be a perfect body that is made and machined for the sole purpose of doing the interior. So they actually can check to see if there's a problem with the interior because they got a perfect buck for all the pieces. And then I got hand applied, those are very cheap, but they're not as fast or not as reliable, and depending on the complexity of the part, may not work at all. I have coordinate measure machines on the left. I just can put my part on my table and measure it. I have things like laser trackers that can go great distances. I can go 300 feet on that laser tracker and be accurate within a couple thousandths or less actually. So we just got to have a plan for what kind of tool and the frequency so I can make sure we're going to be things covered and the budget is there to use those tools properly. So now that I have my points, I got a plan, I actually got to develop my checking systems, actually build those things, right? So PLM purposes, I'm going to talk about CMM programming because that's one of the few that I can do. But, NX has a great tool inside it, Siemens NX, that I can do my programming. If I know my measurement points and I export my PMI with those measurement points in here, I have their names, I have their tolerances, and I can write my CMM program very, very quickly because of the automation in the tool, because I have all that information in there. I'm not relying on a operator to type it in. Here we have an example. This happens to be where I'm doing a turbine and I'm basically making checks along this edge. So you can see all my points there that are in my PMI. And now I'm just going through the face and actually finding the exact coordinates because the CMM probe knows the center of that red ball. It doesn't know where the surface is, so it has to offset it and know the normals. So that's why it needs the faces. And it's going through and actually now creating this program for all these points. And it's all coordinated and automated through NX. Then we get into inspection. So I have my plan, my objectives, I have my GD&T, I have my gauges, and then I got to inspect it. And one of the things through PLM tools, I'm going to talk about a tool called DPV, and that's another Siemens tool. And it can use Teamcenter, it can do a standalone, but in Teamcenter it's very powerful. It's a common reporting system that is readily available to all. It is a tool that takes any type of electronic input and defines it in a common reporting process so everybody can see it. Statistical information. If I go into a coordinate measuring machine room, I can pull up a report for part 1. I can pull up a second report for part 2 and another one for part 3. But I usually don't get the statistics between all the parts and see trends, right? The other great thing about this is I can view all data from all plants and then all suppliers, right? From my seat in my office, with a tool like this, DPV, I can actually just log into my plant in South America. I can log into my plant in Asia. I can log into my plant 2 miles from my office and see what's happening, what's going on, what the data is. So they have a problem, I can access the data. It's all related and given to me, and it's graphical versus just textual. It's graphical on a few points, You know, we have those names that we have for those coordinated measuring points. I don't know what that point means unless I got a secret decoder ring, but it points to it. It actually points to where the surface is being measured or the hole is. So I can see what it is. In addition, you're going to see this here, I can actually see how parts are changing as a system. So let's take a look at this. So I can actually get summary reporting. So I can actually see this. There's an interactive display here that's all, I'm going to say 3D CAD oriented, but there's passive ways to do this. That report that I see there, I can have published every night as a PDF. That way, anybody who doesn't have this tool or know how to use it, just log on to the intranet, find that PDF, and see the report. You know what's going on. It can be sent to the station or monitors for that line or that, you know, that tool that's actually making the part, so everybody can see it. There's reporting dashboards, so I can actually see how well the parts are doing, and I can get summaries for parts. How well did a part do all by itself? You know, I can get statistics for individual points. I don't have to run separate SPC programs. I don't have to pull it into Excel. I don't have to do any of that stuff. It's all there waiting for me to see. So here I'm going to grab a 20-part sample, and I have a couple of choices here. I'm turning it all on and off to make sure I get the rate I want. And I hit OK, and I can actually get the data to show up on screen. And you can see those arrows, the red arrows and the black arrows, showing me order of magnitude. The length is just kind of showing me where it is. And you notice the reds are all in that northeast corner of the part. So something's going wrong. It's coming out of spec. So I can actually see data. I can parse through it. I can parse through it point by point through all the different samples. I can find the offensive ones if that's the case, or if I got one that's good and one that's bad, I can see it. I can highlight them, pull them up on the screen, and then report on them. And you'll see, you know, I got that upper one that has red in it, which is bad. Why is it only in that upper red corner? You know, now I got tools to help me figure it out. It's all about root causing and trying to figure out what the problem is so we can make good parts. There's a tool in there for single part reporting, which is great. You notice this is just being run by a tablet. This could be a mechanic on the floor. You can see here this part's twisting. It's down on the left and up on the right. So I can actually see what's going on, you know, and for that one part. So I can actually start using it to root cause my problems. And this is just done with a tablet over the web inside the plant. So it doesn't have to be a fancy computer. It's web-based, or it can be, you know, PDFs that anybody can view. Then we have things that do graphical by part. So you can see here, this part is twisting. You know, the red lines there are one build. So that one build shows where these parts are. So, you know, the reason what you're seeing is twisting is from build to build to build. So what's going on here? I can actually start looking at this and querying it. You're noticing that blue area up on the left is going up and down, but it goes up when the bottom twists in. When the bottom twists out, that goes down. I can actually see this relationship, and I don't have to look at the numbers of the data. I mean, traditionally, we've always had to look at data by the point and then try to guess that this is going on and figure it out. Here I can see it. I don't even have to know what the numbers are. I got to find out why this is twisting, you know, and then I can fix the problem and, you know, make good parts. You know, the philosophy and evolution of quality management systems has been in the past to react. You know, if there's a spill or a scrap piece or any incidents, you contain it. Then, you know, to the present, a lot of folks are utilizing leveraging systems integrated, SPC, stuff like that. But the big thing is in the future to predict and using business intelligence and such. You know, with this DPV system, if I see something going out, I can actually force it to text somebody to let them know it's going out before it happens. And a maintenance person can actually fix it. But what we're trying to do is basically go from, you know, data integrity and reliability to integrity or integration and consolidation, and then recognition and prioritization, you know, trying to make sure we're getting it found and fixed before it becomes an issue. So, question, how do you get your quality data?
Looks like our top answers. I go to the QC room and talk to Bob.
Yep, when I worked for a large automotive manufacturer years ago, and I knew all the QC managers on a first name basis in all the plants I went to visit, because that was the first place I went in there was to talk to those people. And and a lot of times though, when I got the data, it was individual reports, and then I had to take that data and go to Excel and type it in so I could do statistics on it. So, those are very common situations there, and I was talking to a customer the other day. They're saying, well, how do I use this data into doing something? And what they got was CP, CPK, and range numbers. Somebody did statistics, but gave them no data, and so they didn't know what was going on. And they didn't know that these 2 points moving up and down were going up and down in parallel of each other, or they were twisting and, one go up and one go down. They couldn't tell that because they didn't have the data that supported it. They just had ranges. So, how you get the data and dissect it is very important, and having the right tools will make you solve the problem and get your parts running good or better faster. Okay, so root cause analysis. That's the next stage we're going to go into. And, it's basically formed on manufacturing assembly processes. It's both. If they're incapable, we use statistical analysis. There's multiple tools out there. It's data driven. We use designed experiments, analysis of variance. The source of variation could be in the tooling and the equipment, or it could be in the parts. You never know. It could be spindle to spindle, cavity to cavity. If I got molds, I might have 4 molds and 3 of them are good, but one's bad. And that's causing the variation. So I got to figure out why that one is off. But if I use interactive tools, I can find where the problems are and clarify them. So if we start looking at why we do all these steps, the objectives, it's what the consumer wants, it's what we need for our customer, for a supplier, it's our goals that we want to make. With the coordinated measuring points, I can make sure I'm measuring those 3 areas on my finished vehicle. I got the data to support them, and through the inspection, if I have the same data points, I can do root causing. That's why we're doing a lot of these steps, is so I can root cause it. When there is a problem, I have a path to figure it out and fix it. So let's talk about the last step, which is lessons learned. All right. One of the major corporate assets that's in any company is the accumulated wisdom and know-how of the team. Right. We have graybeards, as I call them, that are in the plant that know everything. Right. They know why it works and why it doesn't work. And when they retire, we lose that information. We design similar products over and over again, but we don't know if the prior one was robust, involved in, problems or delays at launch, or caused warranty problems. But we steal the design and reuse it. I worked at a company years ago. You probably figure out who it is. It was General Motors, but we were making an economy car, and we had a hood hinge, and we got the hood hinge in there, and I'm going, well, where did we get that? And he goes, well, we got that off a Cadillac program. And I said, oh, that's great. How did it perform? Well, it had to be good. It was a Cadillac. No, not necessarily, because that Cadillac was being made on the same line as the Oldsmobile and the Chevy. And it's the same worker and the same team, and it doesn't mean it's good. Of course it was. It was a Cadillac, but, so we want to make sure we understand what it is to make sure it can work correctly. So with that said, there's one thing I want you to remember today is this acronym. It rolls right off your tongue, but this is what it stands for. How the heck did we make that same mistake again? Seen it time and time again, where a product team works on something, and I'm in the automotive industry based out of Detroit. Every 6-7 years, we recycle a program, make a new car, right? And I've seen where new cars are being developed, but that original team's all gone. They got promoted, transferred to other departments. They're not there. Worked with a program that was actually making what they call frame rails, and it was basically two pieces of sheet metal that went together, heavy gauge sheet metal, that had all types of shape to it. It looked like a flower pot with a flange around the top. It was just very complex. And they designed it all line to line. Everything was perfectly mating to each other. And I said, well, what if the inside flower pot grows a little bit in width? You won't be able to put it in. Well, that's the way we designed it last time. And that's all I needed to hear. I went and tracked down the team from last time. And they had a launch delay of 5.5 months because they had to retool the pieces to put design clearances between the inner piece and the outer piece in certain areas so it could always go together, because it wouldn't allow any variation. So once we tracked that down and told the new team that, they said, oh my God, you're right. And they saw what it is and they changed it. But nobody documented the lesson learned. And that could have cost months of delay. And, if I have an automotive plant shut down for 5 months, that's millions and millions and millions of dollars that I don't want to spend because I didn't document. So using a tool like Team Center, I can take all this information, document it in there. The next team has access to it. I have my requirements documented in there. I can see what happened, why it went bad, how I fixed it. It's all documented in there. So the 10-step process, the first 3 steps we talk about kind of heavily, they're the key. But if I don't have good dimensional analysis and good objectives, my GD&T are just tolerances. I don't know if they meet what I have to have. My measurement points, if I don't document them and put them on there, I won't have good gauges. If I don't have a plan for how I'm going to check things, I don't know how I'm going to support my build objectives. My inspection can't allow me to root cause it because I don't have coordinated measuring points. They're all interrelated. So, these 10 steps are key. But if I only had to do 3, the first 3 are the big ones. Because if I don't do those, the rest on the bottom, if I make perfect gauges to check GD&T that won't meet my objectives, it's kind of useless. We don't want to say these parts are good, but the assemblies are bad. So these are the 10 steps that I'm talking about. And, what we want to do is make it a good plan. We don't want to gamble. A plant is too expensive to be making bad parts because we're gambling. We want to have a good plan. And if there is any errors in the plan or the build, we have a way to recover. And that is, the whole purpose of this. So with that wraps up this presentation. I don't know if there's any questions out there.
Hey, Curtis, it's Dan. Yeah, we've got a couple of questions. So first of all, is there any examples of a company that is using all 10 steps?
Well, there's quite a few that are out there. I worked at General Motors, and their body design group uses these 10 steps all the time. They call them different things, but they use these 10 steps. I know companies that have 8-step processes. It all depends on how you want to slice and dice it. But there are a lot of large companies and a lot of small companies because they found they make money doing it this way. It's kind of funny. The middle-sized companies don't always do it. And they're the ones that we have the hardest, conversations on why it's value added. It's amazing. They think it's a cost versus a value.
Okay, thanks. What's the biggest challenge to implementing this 10-step process?
Well, the biggest challenge is getting buy-in at a corporate level, because we're talking about making sure that the manufacturing team, the product team, the quality control team all buy into it. They all know what the other teams are supposed to give them, so they're not, they're getting what they need, and making sure everybody knows what it is and buys in is very hard, to do some companies, because I think that's the biggest stumbling block.
Okay, and the last question: where do we start?
Where do we start? Well, there's many ways to start. We'd love to counsel you. It all depends on what you already have in place. If you have a very strong quality control program and you have a lot of this information, making sure that conversation goes up front. It's kind of ironic. I've worked with companies that are in the manufacturing, teams come and contact us, and they ask us to do GD&T analysis, 3D tolerance stack-ups. Something you think the product team would do. The manufacturing team wants it because they want to make sure they have a chance to make the design, because they don't have trust sometimes. It's that over the wall syndrome. This team does it, throws it over the wall, and the next team does it, throws it over the wall. They want to make sure that they can actually hit the ground running, because the manufacturing team sometimes are the ones who make it work. They make it in spite of engineering. They have to make the thing produce and go out the door. So, they want to make sure they have a fighting chance. So it's just kind of different how every company is different how they're structured. But we'd love to talk to you, and there's many different strategies to do that.